Alrighty. Hello, class. We're not going to be playing games right this moment. Probably after this. I actually have to leave for class in roughly an hour. So I'm going to eat at one point, which means I'm not going to do this for up to an hour's amount of time. Let's say it together. I am not going to be doing this for up to an hour's time. If an hour passes, or if it gets close to an hour and I'm still doing this, I will commit atrocious crimes. Okay, so you're probably wondering what's going on. Well, I am failing Calculus 2. I took Calculus 1, if you can find my oldest video regarding back to it, about 3, if not 4 years ago. During that time, I was pursuing a major involving math. When I got to digital logic, I found out I can't do this major. So I changed majors that dealt with something that doesn't include math in the slightest. I graduated from that major, got my degree, realized I can't move out of my parents' house until I make money. I can't make money until I get a job. The major that I graduated from offers jobs, but these jobs don't pay well. We were warned of this when I was in the major, and I still went through with it. I am not great with making decisions. So, now, we are back in math from Calculus 1 to Calculus 2. And there's still a lot that I don't understand. I don't know if you've realized this, but I am not great at making decisions. So, what we are going to be doing today, we being you and I, if you stick around to listen to this foolishness, we are going to be working on the first chapter of the class that I'm failing. It is currently 2:13. This recording has been going on for 2 minutes. I will end this recording in 30 minutes. So when 32 minutes pass, this recording will end. It will not be edited. You will be watching 32 minutes of me ramble. Welcome to class. Okay, let's get started. Section 5.5. You're not going to see this. All right, I'm just going to be reading this out loud. As noted in the first section of this section, there are two kinds of integrals. And to this point, we've looked at indefinite integrals. No, we haven't. It is now time. Man, is this part 1? I guess so. Now it is now time to start thinking about the second kind of integral. Definite integrals. However, before we do that, we're going to take a look at the area problem. The area problem is to definite integrals what the tangent and rate of change problems are to derivatives. I don't know what a derivative is, or what the tangent and rate of change problems are. I am cooked. The area problem will give us one of the interpretations of a definite integral and will lead us to the definition of the definite integral. To start off, we are going to assume that we've got a function, f of x, that is positive on some interval, a, b. What we want to do is to determine the area of the region between the function and the x-axis. It's probably easiest to see how we do this with an example. So let's determine the area between f of x equals x squared plus 1 on 0, 2. In other words, we want to determine the area of the shaded region below. Alright, let me show you the shaded region below. This is a graph. Don't judge it. This is 5. Don't judge it. This is 4. This is 3. This is 2. This is 1. And this would be 0. 0 would also be here. We'll drag it this way. This is 0.5. This is 1. This is 1.5. This is 2. Don't judge it. You're probably wondering, how did I get this graph? It's in the book. I did not make this up myself. Now we will stretch it. It looks something like this. Caps at 2. Don't judge it. Here's x. This is y. Let's continue. Now at this point, we can't do this exactly. However, we can estimate the area. We will estimate the area by dividing up the interval into n subintervals, each of width. You're probably wondering what that means. The book says that this is done like this. Triangle x is considered to be delta x. Delta x is the width of the graph. The width, I'd assume, would be this. Am I correct? I don't know. Now, let's hide this and start on a new layer. Delta x equals b minus a over n. Then in each interval, we can form a rectangle whose height is given by the function value at a specific point in the interval. We can then find the area of each of these rectangles, add them up, and this will be an estimate of the area. It's probably easier to see this with a sketch of the situation. So let's divide up the interval into 4 subintervals and use the function value at the right endpoint of each interval to define the height of the rectangle. This gives, we're going to see something. Don't be surprised. I'm going back. Well, here's what they did. At 0.05, we hit the line. This line will be met at a little over 1. Now, at 0.1, we hit the line. This line will be met at 0.5, but we can't cross it like that because this height, this width, if you will, is 0.5s, whereas this is 1s, so we have to do 1 to 0.5. Why? The book never tells you. God, I hate math. Now 1.5, we go up. We stretch it over like we did 1 to 0.5, and we connect it. By now you should be noticing a pattern. We're going to keep connecting points. 2, we'll run it to the line. The line is all the way up here. This line that I just drew was bad. Don't judge it. We're going to carry it over and bring it down. These are the rectangles shown in the graph. The graph is cleaner, but you understand what's going on now. If you don't understand what's going on now, you are cooked. Note that by choosing the height as we did each of the rectangles, we'll overestimate the area since each rectangle takes in more area than the graph each time. Now let's estimate the area. First, the width of each of the rectangles is 1/2. The height of each rectangle is determined by the function value at the right endpoint, and so the height of each rectangle is nothing more than the function value at the right endpoint. Here is the estimated area. What did all of that mean? I don't know. Time for a new layer. They're showing us the estimated area. A, I'm assuming would be area, to the R, whatever that is, equals 1/2 because it's 1/2. Why? I don't know. My assumption would be that 0.5 to 1 is 1/2. So 0.5 plus 0.5 makes 1. 1 plus 0.5 makes 1.5. 1.5 plus 1.5 plus 0.5 makes 2. 0.5 equals 1/2. My professor prefers that we work in fractions, and does not want us working in decimals. I don't own a calculator. I cannot do decimals. I haven't taken Calculus 1 in 3 years. I don't know how to do fractions. I am cooked. Back to the problem. AR equals 1/2 times F. They have replaced X because it is usually f of X, meaning a function, with f of 1/2 plus 1/2 times f of 1 plus 1/2 times f of 3 over 2 plus, we just did this, why am I choking, 1/2 times f of 2. You're probably wondering, what am I looking at? I have the same question. My assumption would be that our delta x must have been 1/2 because the width of the rectangles was 1/2 and the width is the delta x. Therefore, the delta x is 1/2, meaning that this 1/2 is delta x. So 1/2 of x, of f times x, delta x replacing x being 1/2. So 1/2 of f working on 1/2 plus 1/2 of f working on 1. You're probably wondering, why is this 1? We touched on this in class. The book does not touch on this. I'm assuming because they assume you know what they're talking about. I am going to teach you this little bit. You are lucky. This is one of the only things I actually understood. When you do delta x, it equals 1/2. The idea is that you will do 1/2 times your function, which apparently x was 1/2, plus 1/2 times your function. In this case, it's 1. If we were to go back to the graph, which I will show you, this is 1/2. I don't know if you can see my cursor, but I hope you can. 0.5 is 1/2, then 1, then 1.5, then 2. If we were to go back, 1/2, then 1, then 1 over 2, which gives 3 over 2, must be 1.5. How do we know that 3 over 2 is 1.5? I'm glad you asked. I am going to be opening up a calculator on my computer in another tab you cannot see, as most teachers do when they teach. 1 times 1 over 2, which would be 1/2, will give you 1.5. Nope, that is a lie. It will give you 0.5. Oh, I see. No, it doesn't. I need another calculator. Let's use a scientific. I'm going to Google and I'm typing in scientific calculator. The first link is Desmos, DESMOS. Now I will type in 1 times 1 divided by 2, which will give me 0.5. That would be 1/2. Where did we go wrong? I multiplied it. We're not multiplying. I know f times 1 over 2 would look like a multiplication, but if you do 1 over 2, 1 divided by 2, 1 divided by 2 plus 1 divided by 2, you get 1. So then we do 1 divided by 2 plus 1, you get 1.5. Okay? Now if we go back to Google and we type in 1.5 as a fraction, we get 3 over 2. How did we convert this decimal into a fraction? I don't know. How to convert decimal to fraction. Place digits after the decimal point in the numerator and use the corresponding place value as the denominator. For example, 0.75 becomes 75 over 100 because the 5 is in the hundreds place. We don't have time for this. This will be used in another lecture. We have 15 more minutes. Let us lock in. I accidentally closed the link. I have to reopen it. Okay, but as you can see, this is how we get the numbers. They're shown on a graph. They have already been graphed. 3 over 2 is just 1.5. 1 over 2 is just 0.5. They turn them into fractions because they're stupid. Let's continue. Okay, 1 over 2 times 5 over 4 plus 1 over 2 times 2 plus 1 over 2 times 13 over 4 plus 1 over 2 times 5. Now you're probably wondering, how did we get this? To answer your question, I have no idea. How did we get 5 over 4? And we lost the F. How did this happen? Let's look back at the question. The height of each rectangle is determined by the function value at the right endpoint. And so the height of each rectangle is nothing more than the function value at the right endpoint. My assumption is F would have to be something in regards to the right endpoint. But we can't assume. For this video, we must do the work to understand. So how do we go from 1 over 2 F times 2 to 1 over 2 times 5? This book does not explain it. That is something that I have found a reoccurring theme in. None of these math books explain any of what it is you're supposed to be doing. It is very frustrating. If the screen looked different, it's because I just took a screenshot. I'm uploading this problem into a cheat program, a program that gives you the answers and breaks down what it is you are seeing. I am now telling the AI to explain. The AI says, what we just put in represents an approximation of the area under a curve using the right endpoint Riemann sum with a specific partition. The function f of x is evaluated at the right endpoint of each subinterval, and these values are used to calculate the area of rectangles. Then, these rectangular areas are summed to estimate the total area under the curve. In this case, the interval is divided into subintervals of width, and the function is evaluated. So we've done that. The values of f of x at these points are the values of f of x. So that would mean that we're missing something the book assumes we've already done. We haven't done it. You know what this means, right? Where my professor has left us to answer is completely incorrect. We cannot use this because we haven't been taught it. So now we must go all the way back to the beginning of the chapter to figure out how to answer for this. Thank you guys for watching. Now that we know what we have missed, we must start over at a new beginning. I will see you then. I'm going to eat.